So this is Mr. Sand. I'm going to tell you about periodic trends today. The first thing I want to do is I just want to define the trends that we're going to be talking about. One of them is called the atomic radius. Atomic radius. And the atomic radius is just the distance between the nucleus and the outermost electron in the atom. The outermost electron in an atom. And we'll just say also that it's in a ground state. In a ground state. Because if it's excited, then the electron's going to be going up to a higher energy shell, and it'll be farther away. So we'll just say in a ground state here. So this is, if you were going to draw an atom, there's an atom, and then here's its various shells around it. If you've got an electron here, it's the distance between the nucleus and the outermost electron. And let's just say this is like lithium right here. We've got 3 protons in the middle, and this is the distance between the protons or the nucleus and the outermost electron in lithium. That's the atomic radius. So it's the size of the atom. The other trend that we're going to talk about is called ionization energy. That's kind of strange. Ionization energy. Ionization energy. This is the energy required to rip away an electron. Required to rip away an electron. There's something we call first ionization energy and second ionization energy. When I say ionization energy, I'm just talking about the first one. That's the first electron that you remove. If you're going to remove a second electron, that's just called the second ionization energy, and there's a trend for that as well. But we're just going to talk about ionization energy, so it's just the outermost electron, the valence electron that we're going to be ripping away here. So it's the energy required to rip away an electron from an atom. So again, if you have lithium right here with, let's say, 2 electrons right here, and there's an electron in the next shell, the energy required to rip away, so there's some energy that's required to rip away that electron. The energy required to do that is the ionization energy. And you might be thinking to yourself right now, well, Mr. Sand, if this has a greater effective nuclear charge than another atom, then it's going to be harder to rip away. And you're right! Okay, so the last one fits in with ionization energy. It's called electron affinity. Electron affinity. And this is simply the attraction of an electron to an atom. The attraction of a rogue electron. Or the ability of an atom to attract. Let's just call it a rogue electron. This is an electron that's outside of its normal electron. So if an atom is just sitting around here, again, lithium, and it's got its electrons right there. I'm not even going to draw the energy shells. And this nucleus right here has an attraction for a passing by electron. It's just going by, and this electron is just moving by. And then if it's attracted here, if it's very attractive, it's got high electron affinity to this nucleus. So there's just electrons just passing by, and then it goes high, and it goes towards the nucleus, and that's a very strong affinity to the nucleus. Affinity means attraction to, so it's electron attraction, really. So the attraction that an electron feels when it passes by an atom, that's the atom's electron affinity. Whew. Okay, we've got all the trends that we're going to use today. And I should also say that electron affinity and electronegativity are very closely related. So sometimes you'll see this word electronegativity, and you can treat it in this class as the same as electron affinity. Okay, so we've got an atomic radius, which is the size. ionization energy, which is the energy required to rip off an electron, the valence electron, and then finally electron affinity, which is an atom's ability to attract a rogue electron. So with that being said, let's take a look at the trends, and then we'll explain the trends. So first we'll just look at the trends, and then we'll explain them. Here they are. Okay, so as you go, let's break them down into across and down. As you go across each period, so from this is what I call a period, so here to there, going across the periods like this, going across the periods like this. Oops. And we're going to ignore, by the way, we're going to ignore these guys over here. They're the noble elements. They don't play nice, so they'll just be left out of our discussion for today. So as you go across the periodic table, there's going to be a trend, and then as you go down the periodic table, there's going to be trends as well. These arrows might get confusing, but we'll see what they mean in a second. So as you go across the periodic table, you'll see a weird trend. You might be thinking, okay, so since we're adding a proton as you go from this element to that element, you're going to get a bigger atom. But in actuality, you get a smaller atom. What? That's crazy. You go from left to right here, and you're going to get smaller and smaller until it gets the smallest as fluorine? What? Yeah. Now let's think about why that happens. If you got... Oh, maybe I can show you a little video here. Yeah, let's try to show the video. Okay. I've got a video right here about this. This is great. Trends. It's going to start up as our slideshow. Okay, that's all right. That's not okay. We need a video. There it is. Okay, I'm just going to erase that. Okay, so let's just go through the video. So there is showing you the different shells. Oh, I haven't told you about this. So the shells of an electron, you can think of each row in the periodic table as a new shell, but there's a little exception here. Like, that's not all shell 4. That's not all shell 5. That's not all shell 6. It's going to get a little bit funky here in a second. Okay, yeah. Actually, these, okay. Let's just ignore what I just said there. You don't need to think about the periodic table in these terms. It's a little bit different than what I just said right there. Let's go into this discussion. Okay, great. So here's a nucleus. It's got some electrons around it. There's one electron, and then there's a next element up. Okay, so I wanted to show you this. I wanted to show you this animation right here. So you've got a nucleus, and it's got a certain number of protons. Let's say it's just got one proton and there's one electron. Now, compare that attraction that this electron feels towards its nucleus. You can calculate it as the effective nuclear charge pretty easily. It's just going to be the number of protons minus the core electrons, and there's no core electrons. So this is 1 minus 0, and the effective nuclear charge is 1. Okay? Now, let's go into the next element, which would be helium, where it has 2 protons, and it's got 2 electrons. So in this case, these electrons are going to feel more of a pull. It's going to feel 2 positive charge because they're all about in the same energy shell. So they're going to be more attracted to this nucleus. And since they're more attractive, and with the effective nuclear charge, you can calculate the attraction. It's going to be the number of protons, which is 2, minus the electrons that are inside these electrons, and there's none of them. So it's going to be 2 minus 0, which is 2, which is more than that previous element that we just saw. So these electrons are going to feel more tug towards the nucleus, and they're going to be pulled in, as you see right there. And because they're pulled in towards the nucleus, they feel a greater effective nuclear charge. This is a very blurry picture, sorry about that. But since they're going to be pulled in, they feel a greater effective nuclear charge. They are a smaller atom now, because these electrons were the outermost electrons. So the overall size of this atom has now shrunk because it feels greater effective nuclear charge. Okay. So as you go across the periodic table, yeah, you see that these atoms get smaller and smaller and smaller. So going left to right across the period, the size says smaller there. Electrons are in the same energy level, but there is now more nuclear charge, effective nuclear charge. So the outermost electrons are pulled closer. That's exactly what I just said. All right, now going down